Hello everyone and welcome to our session in this video for Physics to 10. Today we will solve a lot of important problems that are really beneficial for the exam. This video is part of a series which is an initiative by the Cultural Club of the South to support students. And let's start. Here we have some constants that we will use. Okay. We have multiple choice questions. Okay, let's zoom out. We have multiple choice questions, 14 multiple choice. We'll solve it together. Okay, let's see number one. A brass rod is 75.2 centimeter long and an aluminium rod is 55.8 centimeter long at an initial temperature of 25 Celsius. They are placed with a gap of 1.5 centimeter between them, and the distance between the far ends is maintained at 132.5 centimeter. The temperature is raised until the rods just touch. The coefficient of linear expansion, we are given alpha brass and alpha aluminium. At what temperature do the rods touch? Okay. Here is the L final that we needed, the final length. The final length is equal to what? Is just equal to L0, or let's say L brass plus delta L brass plus L aluminium plus delta L of aluminium. Okay. Let's just remember together what's delta L. For 1D, the linear expansion, that's delta L, is equal to L0 of the material times alpha of the material times delta T. And alpha is alpha, that's given here. For 2D, the delta A is equal to A0 times, I remember it's named gamma, times delta T. But what's it gamma? Gamma is 2 alpha, just this. And for 3D, the delta volume is V0 times beta times delta T. And here beta is just 3 alpha. Okay. This is just to remember the expansion when temperature is raised. Okay, let's remove it for now. Okay. Then 132.5 is equal to how much? It's equal to 75.2 plus 75.2 times 18, yes, times 10 to the power of minus 6 delta T plus, okay, I will continue, I will continue here, plus 55.8 times alpha of the aluminium, 23 times 10 to the power of minus 6 delta T. From here we can solve it for delta T. It's just mathematics here. Okay. Over 72. This is 72 point. Okay. To not be confused between the time, the multiplication, and the virgule. Okay. Plus 55, okay, times 23 times 10 to the power of minus 6. It will be approximately 568 Kelvin, to say Kelvin, okay. Then here, the T final, what we need, minus the initial, because the two rods have the same temperature, initial temperature, 25, then we can do it that, take it delta T as one variable. It's okay. From here we can get T final is approximately 590 okay, we can get it 590, but why it's in Celsius? Oh yes, it's in Celsius, not in Kelvin. Okay, Celsius. That's C. Okay, number 2. How much water remains unfrozen after 45.3 kilojoule of heat is removed from 300 gram of liquid water initially at 0 Celsius? Okay, let's remember something. Q, or the heat, have two formulas in chapter 18. It's either MC, C is specific heat, times delta T, or Q is equal to ML for phase change from liquid to solid, solid to liquid, liquid to gas, or gas to liquid. We use this. And here what we have? We have phase change from liquid to water to ice. Then we can get M frozen. It's just Q over L. We are given L and we are given Q, then we can get it. It's just mathematics. Okay. To get the answer in gram, we do times 1000. Okay, then we subtract from here 1000 from the latent heat of fusion, and we can get the number here. It's 136 gram of frozen water. But how much water remains unfrozen? M of unfrozen is just M initial, M0, minus M frozen. That's 300 minus 136. That's equal to 164 gram. And that's D. Okay, let's continue. Thermometer of mass 0.06 kilogram and specific heat capacity 600 joule, okay, reads 10 Celsius. That's what? That's the initial of the thermometer. It's immersed in 0.25 kilogram of water and they reach a final temperature of 40 Celsius. 40 Celsius is the final for both thermometer and water. What was the initial temperature of the water? Here we have just one unknown, that's the initial of the water. Here, what we do? We need to say that it's isolated. Isolated to have conservation of energy. Delta Q total is equal to 0. Then delta Q of thermometer plus delta Q of water is equal to 0. Then M thermometer, C thermometer, times delta T, we say now delta T, or 40 minus 10, because the final temperature of the thermometer is 40, initial is 10, plus M water, C water, 40, because it's the final temperature of the both thermometer and water, minus T initial, it's equal to 0. We can get from here T initial, it's just, here it's 30, okay, 30, okay, plus 40, and WCW, over MWCW, we get that's approximately 41.1 Celsius, and that's C. Okay, okay, let's continue. A cube with edge length r, a sphere of radius r, and a hemisphere of radius r, all at 300k, okay, are placed in an environment at 350k. Rank the objects by the net rate at which thermal radiation is exchanged with the environment greatest to least. Hemisphere, okay. Here we need the initial some information that's it's same material. Okay. The three objects are from the same material. Why we need this? Okay. First, let's put the formula. P, it's equal to what? P is the radiation, the thermal radiation, net rate of thermal radiation. It's sigma times A, the area, times E, the emissivity that's between 0 and 1. It can be like this, yes, equal. Times T final to the power of 4 minus T initial to the power of 4. But we are given that same material. What same material mean? That they have the same emissivity. Because they have the same emissivity, then this is constant between the three. And sigma is constant between the three also, because it's constant between all objects, not just of the same material. T final, T initial, 350, T final is 350k, T initial is 300k. It's the same for all three objects. Then what's the difference between them? The A. Okay. Let's draw a sphere, but in 2D. Wait, that's not a circle. That's okay. That's oval. Okay, like this. Okay. The area of a sphere is what? It's 4 pi r squared. Right. Okay. The area of hemisphere, let's name it like this, it's just the half of the area of the sphere. That's 2 pi r squared. Okay. The area of a cube, it's just 6a squared. A is okay, 6r squared. Okay, what we have here? Area of sphere, that's 4 pi r squared. It's approximately 12 point something r squared. And here, this is 12 point something. This is 6 point something. And this is 6. Then, from the greatest to least as area, we have the greatest is the sphere, after that the hemisphere, after that the cube. And what we see here, the relation between the area and the power, that they are proportional. That means when A increase, P increase. Then, because we have a sphere is greater than a hemisphere greater than a of a cube, then P of a sphere is greater than P of hemisphere is greater than P of the cube, and that's E. And now let's continue. A Carnot engine whose low temperature reservoir is at 20 Celsius operates with an efficiency of 35%. Okay, by how much should the high temperature reservoir increase to achieve 50% efficiency? Okay. Let's just write it. E is equal, the definition, it's the work done by the system over the Q absorbed from the hot reservoir. Okay. But what we can write, the absolute value of the work, it's just It's just because we have here the engine, okay? Here's the engine. We put QH. We get from here QC. If W come from here, what's W? Is absolute value of QH minus absolute value of QC over what? Over absolute value of QH. That's what? That's 1 minus absolute value of QC over absolute value of QH. Because it's a Carnot engine, then it's 1 minus TC over TH. And we can formulate, or we can formulate a formula for the TH. That TH is equal TC over 1 minus E. It's not important. We can solve it normally by this, but this is just a new information that I give you. Okay, from here, for E, okay, just to write properly. For E equal to 0.35 for 35%, we get TH, okay, and not something. TC is 20 Celsius, but TC must be in Kelvin. It's 20 plus 20, 273.15 over 1 minus 0.35. It's 451 Kelvin. Okay, let's continue. We get TH 451K. We can solve it normally from here. We'll get TH prime. That's TC over 1 minus E prime. E prime is just the 50%, 0.5. Okay, we get that's just to write it. Over 1 minus 0.5 is 0.5 equal 580, no, 500, 586.3 Kelvin. From here, delta T is approximately 135K. That's A. Okay. Let's continue here. A monoatomic ideal gas expands from 1.2 meter cube to 2.8 meter cube at constant pressure. We are given the constant pressure. Calculate the change in internal energy of the gas. Okay. Here we write the formula. Delta E internal is NCV times delta T. We have here the ideal gas law. PV is equal to nRT, right? Right. Then T is equal to PV over nR. T initial is equal to P initial, V initial over nR. T final is P final, V final over nR. Right. And CV for a monoatomic gas is 3 over 2R. Right. Then here we have 3 over 2 nR times P final, V final minus P initial, V initial over nR. We can simplify nR, and we have that P initial and P final is the same because it's at constant pressure. Say that here. V final minus V initial. We calculate it. We get 360,000, but we write it like this. That's D. Okay, let's continue. An ideal gas initially at 2 atmospheric is compressed isothermally to 1/3 of its initial volume. What is the final pressure? What we have here? Isothermally, right? What isothermally mean? T is constant, or by other words, T initial is equal to T final. And what we say here, it's ideal gas. What ideal gas mean? That we can use ideal gas law. PV is equal to nRT. And always PV over T is constant. Always for any ideal gas, monoatomic, adiabatic process, isothermal, always PV over T is constant. Then here P final, V final over T final is equal to P initial, V initial over T initial. But what we said here, T initial and T final are the same. We can simplify it. We can get what we need. We need P final. P final is just P initial times V initial over V final. That's 2 atmospheric. V initial is V initial over 1 over 3 V initial. We simplify it. And we get here 6 atmospheric pressure. And that's C. Okay, let's continue here. For one complete cycle, as shown in the PV diagram below, which of the statement about the change of internal energy delta E internal and the net heat is correct? Okay, let's see here. What we have here? Okay. Here we have cyclic process. What cyclic process mean? We go from initial point and we go back to this point. What that mean? That mean delta E internal is equal to 0. And from the first law of thermodynamics, delta E internal is equal to Q minus W. Then Q is equal to W. First, delta E internal is equal to 0, then this are not true. Yes, we can say if this is true or not. But let's continue. You cannot tell. It depends on the sign. It depends on the sign of the work. That's true. It depends on the sign of the work done. But from here, what we see? We see that's going like this. What that means? That it's compressed, then it's what? It expand. If it compressed, then it expands, then the work is negative. And because work and heat have the same value, then Q is negative. Then it's E. Okay, let's continue from here. Assuming a 150 watt light bulb acts like a perfect black body, emissivity E equal to 1. What is the temperature of the filament if its surface area is 3.74 times 10 to the power of minus 5 meters squared? Okay. Here they must say what's it's the from here the maximum temperature, because we can have in some pieces of this filament a minimum temperature of temperature less than T max. Okay. We just put the rule. P is equal to sigma times area times emissivity times temperature to the power of 4. From here, we can say that the temperature is the fourth root of P over sigma times A times E. And we just put values. Yes, we just put values. Let's put values. This will take time, but this time is counted in the exam. Okay, times 1 the emissivity. We get that's approximately 2900 Kelvin, and that's E. Okay, let's continue. Is there something here? No, it's correct. Okay. A monoatomic ideal gas undergoes an isochoric process followed by an isobaric process. The gas starts at T initial, okay, T1 300K, P1 equal 1 atmospheric. The final volume and pressure are double the initial volume and pressure, respectively. Okay. We can conclude that V final is to V initial, P final is to P initial. We use, because it's an ideal gas, we can use that PV, that's not you, that's V, wait. P final, V final over T final is equal to P initial over V initial over T initial. Okay. Then T final is just T initial times P final, V final over P initial, V initial. That's 300 times 4 P initial, V initial over P initial, V initial. This is just from here. V final is to V initial, P final is to P initial, then P final, V final is 4 P initial, V initial. We subtract this, okay, we get 1200, 1200 Kelvin, and that's D. Okay, let's continue. A refrigerator with a coefficient of performance COP of 3 removes 500 joule of heat from the cold reservoir per cycle. How much work is done per cycle? Okay, let's just remember with us. What's the concept of a refrigerator? Here we have TC, okay, or QC, okay. We put work to get QH. In a refrigerator, we benefit from this, that it's cooled down. Then we use it to our beneficial for a refrigerator. In a heat pump, we use this heat to beneficial from the heat given. For that, we need a lot of work to get this temperature very, very high, or not very, very high, but high to some level. Okay. Then, COP is what? Is the Q entered for a refrigerator, it's QC over W. For a heat pump, it's a QH over W. But in a heat pump, okay, let's, this is an additional information. Okay, for a heat pump, it's QH over W. But from here, what we can say is that QH is QC plus W, right? Yes. Then, if they give us QC, they say heat pump with a coefficient of performance of 3 removes 500 of heat from the cold reservoir. They didn't say we get 500 joule in the hot reservoir, then we must implement this. For QH is a QC plus W over W, and we calculate it to get W, okay? But here, it's a refrigerator, then it's QC over W. Then W is just the QC over COP, the coefficient of performance, 500 over 3, it's approximately 167 joule. Okay. And here, let's continue. A Carnot engine operates between a hot reservoir at TH and a cold reservoir. We are given TH, TC. If the engine absorbs 1000 joule of heat from the hot reservoir, what is the work output? Okay. I said before, where here, efficiency is equal to the work over the heat from the hot reservoir, or the heat absorbed by the engine from the hot reservoir. Then we say E is equal to absolute value of W over absolute value of QH. But we said also that's equal to 1 minus TC over TH. Then absolute value of W is 1 minus TC over TH times QH absolute value. That's equal 1 minus 300 over 500 times 1000. And this is 0.6, this all is 0.4, this is the efficiency, 0.4 or 40%. Then it's 400 joule, and that's B. Okay, last two questions. A 100 gram block of ice at 0 Celsius is placed in 500 gram of water at 80 Celsius. Assuming no heat loss to the surroundings, how much ice melts? Okay, here let's just see how much energy can be given by the water. We said before that there is two formulas for Q. Here we will use, because there is no phase change, we will use it for the block of ice, but now for the Q that is given by the water, it's just MC delta T. That's just 0.5, because M is in kilogram times 80. If we calculate it, okay, let's just get the calculator. 0.5 times the specific heat. Okay, we get here, or here, this number, but here we have minus. Okay, we got this number. This is a Q that can be given by the water, but the Q needed by the ice to melt it completely, it's just ml. M is 0.1 and L is just this number we get, that's 33,300 joules. That's needed for what? To complete melt of ice. Then, because we have the Q given by the water is greater than the Q needed by the ice, then all the ice will melt. Then it's E. But here, let's do something in plus. Let's get the temperature, final temperature. We just say delta Q total is equal to 0. Then M W C W T final minus 80 plus okay, plus ml, that's the heat needed to complete melt of ice, plus m of the new water, we will call it ice, sea water, times T final minus 0, because when the ice melt, it's at 0. It's still at 0. From here we can get that T final. Okay, let's do some mathematics. That's T final is equal to 80 MW CW minus ML over MW CW plus M ice CW. It's equal, we can get it. Okay, from here we can get it minus and divide it by 0.1 times, okay, 0.5 times, okay, that's 53.39 Celsius. That's T final. Okay, here we have the last question. Which of the following statements is not true about the Carnot cycle? Okay. It's the most efficient cycle for a heat engine, and that's true. All E, okay. Okay, that's right. Okay. All E of any engine is less of the Carnot version of this engine. Okay? It's less than the current version of this engine. And that's the same for A and E. No, it's the most efficient cycle for a heat engine. That's true because this. And no engine can be more efficient than a Carnot engine operating between the same two reservoirs. That's also true. And here let's say something. E cannot be equal to 1. E can converge or approach to 1 but not reach it. It can't reach it. Because as we said, it's 1 minus Cc over Th, but Tc can't be 0 Kelvin because this is the third law of thermodynamics. Okay, let's continue here. C, it consists of 2 isothermal and 2 adiabatic processes. That's true. B, I forget B. The entropy of the system changes after 1 complete cycle. Let's discuss this. Okay, if we say we have, okay, this A, B, C. Okay, we go from this point, we go to B, then we go to C, then to A. Okay. The entropy depends on the initial and final points. Okay, and as we go from the initial point and come back to the initial point A, then delta S is equal to 0. As more as it's a reversible process, not irreversible, because if it was irreversible, it will go from the initial point and come back to some point that are not the same as the initial point. Okay. Then B is false. Let's see this. The work done equals to the net heat absorbed. It's equal. Okay, here it must be equal to the difference between QH and QC. It must be like this. Okay. Then that's all. Let's review all questions. If there is some mistake. Okay. And here let's give you a formula that I concluded. In an adiabatic process, W is equal to P final V final minus P initial V initial over 1 minus gamma. This is just in what? An adiabatic process. Okay. That just we get it from that's PdV, the integral of the pressure by the volume, and always we have also that's it's P initial V initial to the power of gamma equal P final V final to the power of gamma. That's students always forget this formula and the other formula. This is not known for students, that's just a conclusion. And T initial is V initial to the power of gamma minus 1 equal to T final V final to the power of gamma minus 1, and that must be all what we need. Okay, I hope this session was helpful for you. Any feedback will be very beneficial for us. The PDF will be uploaded to Drive and linked in the comments and the description. And good luck for your thermodynamics exam, guys, tomorrow at 5:30, I think. And goodbye. Good luck.